Okay. Well, thank you for this opportunity to give a talk to both programs. Today I'm going to talk on some symmetric orthogonal polynomials, and whilst I'm actually technically a member of the CAT program, it's two people in the GCS program that have inspired parts of what I'm going to talk about today. RA being one of them. So I'm going to first give an introduction to orthogonal polynomials to familiarise you with things you probably already know, but just to make it sure. Then I'm going to look at two types of weights that are symmetric. A generalisation of the Hermite weight, just this bit here. I have put on an extra term to make it generalised. Then we have this characteristic function here, which the xi can take a number between 0 and 1. And then I want to look at some generalized Freud weights, which take on this form here. This classical Freud weight, mostly studied, has m equals 2. But recently we have obtained some results on m equal to 3 and higher that I think are quite interesting that show it. So why do we want to look at symmetric orthogonal polynomials? Well, having read some papers by Aria, I realized that you need to have some symmetric functions, particularly orthonormal functions. They help in the design of numerical procedures that you want on L2. And whilst the symmetric polynomials I'm going to discuss today are possibly more complex than what Aria would like, they are symmetric and they have some interesting mathematical properties. So, I'm going to consider monic orthogonal polynomials. You could take orthonormal, but I'm just going to stick at monic. So we have the standard definition that we have a weight, and the polynomials are orthogonal with respect to the weight. And one of the most important properties is the three-term recurrence relation. Here, which relates three of them, and these coefficients are explicitly given by these integrals here. Because I'm looking at a symmetric weight, I'm going to consider the whole real line. And so if I look for symmetric weights, then we clearly see that the alpha n is equal to 0, and so I only have to worry about working out what the beta n is. So I have a much simpler three-term recurrence relation, and also the polynomials have this symmetry property here. So if I want to work out the coefficient in the three-term recurrence relation, you can express this in terms of Hankel determinants. Particularly take this Hankel determinant, which is determined purely by the moments of the weight, which are these integrals here. So given the weight W, you work out all the mu's give you the deltas give you the beta n. Very simple procedure. Now for symmetric weights, clearly all the odd ones are 0. And then in a talk in Kent 2 years ago, Evelyn Hubert effectively gave this result as part of her talk, that if you have one of these determinants for which half the coefficients are 0, then you can split it into two components, I'm going to call an and bn, and you have to distinguish whether it's odd or even, and the an and the bn are also Hankel determinants purely in terms of the moments. As we shall see later, this splitting makes a huge difference when actually trying to compute the actual coefficients beta n. It speeds it up considerably, but also I can't get differential equations for the delta 2n or the 2n plus 1, but I can get differential equations for the an and the bn. And given differential equations, I'm much happier solving differential equations than anything else. I can actually get a lot of information about the properties of an and bn. So it has that advantage as well. Now for symmetric weights, we can therefore write the coefficients, the insertion coefficient b to n, in terms of these ans and bn's. This is very simple, it just comes straight from the definition. You just put these in and you get the answers as what you have. So you've got this representation of the recurrence coefficients in terms of these n by n matrices rather than 2n by 2n matrices. Now if we take a weight, a symmetric weight W0, and then multiply by e to the tx squared, which is the case for the Freud weights I'm looking at, then I can write these determinants an and bn as Wronskians in this form here, in terms of the lowest rate mu naught. So all you then need to work out is mu naught, and then you have the answer to the problem. And the proof is entirely trivial. If you assume that you can interchange differentiation and integration, then clearly mu 2k is the k's derivative of mu naught. And so the Hankel determinant then just becomes a simple Wronskian. Very easy to calculate. Relatively easy to calculate. The other aspect about this particular type of weight, this one here, is that the b to n of this weight satisfies this differential difference equation called the Volterra lattice equation, sometimes known as discrete KdV or Kac-Van-Moerbeke ladder, or the Langmuir lattice. So it satisfies this differential difference equation here, and we shall use that later when looking at the Freud weights. Now if you just take a simple example, the simplest symmetric weight is the Hermite polynomial, and if you just simply go through the mechanism of working out what it is, these are what the moments are, this is what the delta n is, then the b to n just becomes a half n. But we knew that already, but that's, so you get the monic polynomials related to the Hermite weight, which are just a scale version of the standard Hermite polynomial. So that's the simplest symmetric weight. Now, as you know, many of you know I do a lot of work with Pavlov equations, so I need to relate what I'm doing to Pavlov equations. I'm not going to go into the theory. These are the 6 nonlinear ordinary differential equations with a, b, c, and d constants. They are transcendental in the fact that general solutions cannot be expressed in terms of known functions. However, Pavlov 2 to 6 have special solutions in terms of the special functions, Airy, Bessel, consonant hypergeometric and hypergeometric, and that is what we shall use. But related to these are 6 second order, second degree differential equations, known as the Pavlov sigma equations. They're in a one-to-one correspondence with the 6 Pavlov equations, in that you can, knowing the solution of one, get the solution of the other. I'm not going to go through the details, I gave that in the master classes I gave in September. So, but it's actually these equations that arise more commonly in all these applications in orthogonal polynomials, rather than the original Pavlov equation. That's why these are the important ones, really. And, as I said, 2 to 6 have special function solutions in terms of the classical special functions. And this is a useful way of actually trying to work out what the recurrence coefficients of certain weights are. In particular, if you look at these monic orthogonal polynomials in the general case, then I've listed some weights here whose solutions or whose recurrence coefficients can be expressed in terms of the special function solutions of Pavlov equations. This one is in terms of Airy, Bessel, parabolic cylinder, you'll see this later. These are all in terms of confluent hypergeometric, and these in terms of the hypergeometric. They effectively arise because the mu naught, the lowest moment, is an integral representation of a special function. And that's how you recognize what it is. And then the special function solutions are all written down technically, normally as Hankel determinants or as Wronskian. So you can make this identification between the two. We'll see an example of that shortly. Okay, so let me first look at this generalized Hermite weight. So if we have lambdas minus a half, and we just have the classical Hermite weight. Now this is a well-studied one, that's been studied a lot, but it is the recurrence relation as the beta n, and the beta n has a -1 to the n, so that the recurrence coefficient varies as to whether n is even or odd. So it's an example of where there's a distinct difference between the coefficients when you are even or odd. And also in this particular case, you can represent the orthogonal polynomials in terms of associated Laguerre polynomials. But again, you have to distinguish between whether you're in an even and odd case. So now I'm going to modify this by putting in this function here, 1 minus xi times the pi function between minus t and t. So it has the effect of making this sort of discontinuous weight, but symmetrically discontinuous. I'm going to take xi between 0 and 1. If xi is 0, I just get back to the Hermite polynomial. If xi is 1, a lot of the things go through, but they're just the details are quite somewhat different. There's a limit case that you have to be quite careful. So I'm just going to strip between 0 and 1. So it's a symmetric weight, so all the odd moments are 0, and the even moments, well, by a change of variables, you get them in terms of the gamma function and the incomplete gamma function, so that I can explicitly get them like this. Now you can write them also in terms of comma functions, but that's sort of a little over the top. You can really just take gamma functions themselves. And in fact, there are two special cases. If lambda is n minus a half, then you can write the moments in terms of an error function and a polynomial times an exponential. If lambda is an integer, then the moments are expressible in terms of associated Laguerre polynomials. These are what the first few are for lambda equals 0, but more generally, if lambda equals m, this is what the nth one actually is. So you can explicitly get them in terms of associated Laguerre polynomials.
So they are the polynomials outside the orthogonal range in this case. They are associated Laguerre. The parameter is less than -1.
Yes, and also the parameter depends on the degree. So it's a very special type of loop. But your point is you can actually write them out.
They are in Zegge's book.
Right. Yes. We can write them as this closed form here, which is quite nice that you actually have to do it. So these are what they actually are. Okay. So we also in this particular case have the fact that the 2k plus 2 moment is the 2k moment with the parameter up by 1. So if in this particular case, it means that the Hankel determinant Bn with parameter lambda is the same as the Hankel determinant An with parameter lambda plus 1. So all I now need to worry about is the Hankel determinant An. And so I can now write the delta 2n and 2n plus 1 in terms of the An and An plus 1. And therefore I can write all these recurrence relations all purely in terms of this Hankel determinant An. Those are what we actually have. So explicitly do it. So what do they look like? Well, this is what the first few plots of the recurrence are. These are the odd ones, and these are the even ones. And I took the parameter lambda to be -1/2. And so they tend to half n Well, they're all going to tend to a half n because I've got lambda to be minus a half in this case, but in general, this is what they do, and it varies whether they're even or odd as to what they tend to. Now, they have exponential decay as you go to, as t increases as well. If you put some more together, you see that they create a nice pattern there. For people who like solitons, it's quite familiar, that kind of thing. Seeing more and more come out. And as you increase the parameter lambda, then the even ones, they all tend to a half n, but the odd ones, they tend to a number bigger as you increase. So they start, the lines start to go up as you have. Let's look at the same kind of pattern. These tend to spread out a bit more as time as you increase the lambda as well. So those are what they actually look like. I always think the pictures of those are quite nice to know. Now, I said I want to look at differential equations for the Hankel determinants. So the standard thing to do is to take the Hankel determinant an and you take a logarithm derivative. Now this one I've taken t times d by dt of the log, and it satisfies this second order, second degree differential equation. It's actually easy to actually verify this. Firstly, you use Heine's integral formula, which changes the Hankel determinant into an n-fold integral. And this has important consequences around the matrix theory. I'm not going to go into that, that's a different story altogether. But that is what you have, is this quantity here, where I've defined it in general. You have an interval, you have a parameter xi, and you have a weight w, and this is what it's defined to be. It's an n-fold integral of what we are.
Isn't the factorial missing?
It doesn't matter because I'm taking a logarithm derivative. Yes, technically there is a factor, there's a constant missing, but since I'm taking a logarithm derivative, I don't care. What is written there correct, it's just not the same definition as in all the literature. That can be different. So, well, Tracy and Widom in 1994 showed that if you take logarithm derivative of a very similar kind of function to what I have here, this was on 0t squared, there on 0z, then it satisfies this equation here, which is a special case of the sigma equation for panel of A5. The reason I could have guessed we were going to get panel of A5 was because we had gamma functions arise from the moments. So it's a special case, so then I just make a simple change of variables in this equation, and I get the equation I have. So now I've got a differential equation, oops, wrong way, for logarithm derivative of an. So I have a differential equation to do, I can do some work on. Now, so what do these functions Sn look like? Well, this is what the first 5 looks like for lambda equal to 0, and this is the 6 to 10. And you can see they all just touch. Really rather curious. Like your kissing polynomials, except that often these kiss more than one. So, but
in the best Hollywood tradition, they kiss smoothly. Mine have political discontinuity.
And they all have this exponential behavior as you go to plus infinity. So that we have this exponential decay as you go to infinity here. So it's I just thought it interesting that that's what the solutions actually look like. Also, the interesting thing is that for small ones, the leading hump is the tallest. When you start to go up further, it becomes the second one. As you increase further, it goes more and more that way as well.
What happens at the kissing points? Is the Hankel determinant vanishing?
don't know. I don't know what exact, but they do. It is an exact point,
Yeah.
as far as you can tell. It is an exact, but I don't know what's actually happening to it. Anyway, here's the drawing. Anyway, so that's what they actually look like.
Meaning that you can say for the first 10, they all kiss perfectly, but for the end,
This is
you haven't
this
proved-
is
it's not proven.
No, I mean this is work I've been doing since I've been in Cambridge.
Ah,
So this is sort of very hot off the press. Trying to work out what these actually look like. I've seen these kind of plots for error function solutions of Pandlevet 4 before, but this is now a Pandlevet 5. So that was that's what we have. Okay. So now what we can have is that you can express the Hankel determinant, or logarithm derivative of it, there's a log missing in there, in terms of the sum of two of these SNs. So we have a way of actually expressing them in terms of the sum of two, where they satisfy here. So we've actually got a way of now, by taking an integral of this, being able to determine what the delta 2n is. But it's going to be different whether it's even or odd. And for many weights that involve a parameter, we can get a single representation, a single differential equation for this quantity here. In this case, for this weight, and in fact for the Freud weight later as well, we can't do that. We have to use it as a sum of two solutions. It's a quite different kind of formulation. You can't get a single nonlinear differential equation for this unless xi is 1. When Chris Cosgrove got one, it was a pretty nasty thing of equation he actually found. Involved second degree and square roots. So now let's move on to Freud weights. Freud weights, I'm going to look at particularly the cases m equals 2 and 3. Case 2 has been looked at for quite a while, the case 3 is relatively new.
going back to that previous one with the S equation, is that a sigma equation?
Yes.
That's one of the sigma equations?
It's you take t to the square root of z. Yeah, it's a sigma equation for Pandlevet 5. So,
Okay.
But again, Peter, one question. So to obtain these equations, the best way is through this integral complicated formula?
I don't say it's the best way.
But is there another way to do it?
You could use ladder operator theory.
I see.
Well, the point is I didn't have to do any work. I just have to look at the paper by
Identify,
Tracy and Widham and write the answer down. I mean, it's called of conservation of energy.
But that's how they had done it before?
No, they did it through a random matrix
That's what I
operation.
thought, yeah.
They did it a completely different way. But I didn't need to derive it because I just had to know what kind of results were available for it.
Thank you.
I mean, that's, there's no point in me deriving it. Typically in the orthogonal polynomials, you'll use a ladder approach to try and generate it. You don't need to do that in this case. In fact, with many of them, if you can actually recognize which sigma equation it actually is, and again, by recognizing what the special function you have, you can then often find the change of variables will actually get you there. I mean, that's how I basically recognize them. It's a matter of then knowing various transformations to get what I have. But this is yes, it is one. So we have other things as well. Right. So let's go into Freud weights. Freud weights are an interesting kind of scenario because if you look at the digital logarithm mathematical function, in the section on Freud weights, they say no explicit expressions for the corresponding orthogonal polynomials are available.
You can fix that up.
Yeah, I'm going to fix it today. I'm going to plot them and give you a mechanism. Now, it can be trivial to actually write them down. It's certainly not trivial to compute them, but in principle, we have a closed formula for it. So that's I have a closed formula for the recursion coefficients. So then starting off, I can generate as many as I want. Okay, so Freud in his 1976 paper was looking at weights of this form here. So I'm going to add an extra term in here. This is actually quite helpful. And they're symmetric, so let's have a three-term constellation. And he found them explicitly in three cases. For m equals 1, which is a generalization of the Hermite. M equal to 2, we get this discrete equation here, which is an autonomous discrete Pandavert equation. I'll say a bit more about that. And for m equal to 3, you've got this fourth order, third degree difference equation. This is explicitly what he did. And he made the conjecture that the limit of Bn over n to the 1 over m was this number here.
Presumably for higher m, that's a higher order discrete Pavlov equation.
Yeah.
Presumably.
Yes. I'm going to say a little bit more about that. You're going to see one. Sure. Okay. So this is what Freud did. Now, I've indicated about discrete Pavlov equations, and the link between these semi-classical orthogonal polynomials, which are the ones that are in effect not classical, and integral equations actually dates back to the work of Shohat and Freud. But it wasn't until Thanasis, Itz, and Kipev in 1991 too that he demonstrated that these actually were discrete Pavlov equations, though they've actually been written down. And in 1995, Magnus looked at this Freud weight and showed that the coefficients were simultaneous solutions of this, which is the discrete Pavlov one. It also appeared in the work of Bonan and Neva in 1984, but also simultaneously solutions of Pavlov 4 for the specific choice of the parameters. So these were the two, they both satisfied both equations here explicitly. And if you actually take this weight here, I'm going to add an extra term on here, then what is shown is that you have this weight, this difference equation, discrete Pavlov, and you've got very specific initial conditions. You have to have these specific initial conditions to generate the solutions you want. You've got a parabolic cylinder function with these very specific things here. And this is what the Freud conjecture gives in this particular value. This beta over the square root of n has to be 1 over the square root of 12. So if you actually look at what these actually are with these specific initial conditions, then they do tend, they take a time for them to converge to get it. So to get these plots, I need to use about 100 degrees of accuracy. So you can actually get at what the asymptotics of those actually are. But if I want to move on to this generalized Freud weight, results I'm going to talk about in these two papers that appeared quite recently. So I'm taking the Freud weight and I'm adding on this extra term here. So now, for this term, I can write the initial moment in terms of a parabolic cylinder function, because that's what it is. You just use integral representation of parabolic cylinder function and actually gets this here. And so the two kth moments are just the kth derivative of mu naught, and the 2k plus 1, all the odd ones, are 0. And if lambda is an integer, then the parabolic cylinder function can be expressed in terms of arrow functions and exponentials. So what I can do, just using the theory I described earlier, is I can get these explicit recurrence coefficients in terms of this Wronskian AN, where the mu naught is a parabolic cylinder function. Again, different for even and odd. Again, we can actually write down a differential equation satisfied by the logarithmic derivative of AN. And here's a second order, second degree, a sigma equation. This was the Pavlov 4 sigma equation. It's not a surprise, we have parabolic cylinder functions which are noted with the special function associated with Palomé 4. And again, I can write down I can write the betas down in terms of this Sn, but not in terms of one of them, in terms of two of them. So I can explicitly write down these all in terms of solution of this differential equation. Now it turns out the beta n's also satisfy Palomé 4, but again they do differ as to whether it's even or odd. So the parameters change between whether you have an even coefficients and odd coefficients. It also satisfies the general discrete Palomé 1, where you now have this 1 minus 1 to the n. Now the interesting thing about this discrete Palomé 1 is that it's called discrete Palomé 1 because in an asymptotic limit it goes down to Palomé 1, but actually only in the case when lambda equals minus a half. When lambda is minus a half, it goes down to discrete Palomé 2. The paper by Craswell and Joshi from 1999 that shows the difference between what happens in the cases when this minus 1 minus minus 1 to the n occurs. Instead of having a single difference equation, you have to write a couple system to do the limit. And the link between these two equations, between the differential equation and the difference equation, are the Backlund transformations for Palomé 4, which are given here, which relates, you can get the bn plus 1 in terms of bn, or bn minus 1 in terms of bn as well. So you have this is what the coefficient actually satisfies in this particular case. And so I can write down the Combs coefficients explicitly in terms of this function, the parabola cylinder function. So you can plot them. After all, in many things that we do, so in soliton theory, we're just happy to plot down the first 2 or 3 solutions, and that's about all we get to plot. We should hear what the beta n's actually are, and they differ considerably between whether they're even or odd. And you've got algebraic decay in the even case, but you've got some algebraic growth in the odd case for the beta n. Having got the beta n's, you can so we can write down, I can actually write down all the asymptotics. I can work out the asymptotics from the differential equation for what the beta n's are to show the difference between the even and odd cases. And you can make various conjectures just based on looking at what the pictures are about monotonicity of the as well. Given the recurrence coefficients, you can then work out the first few actual polynomials. Now, in a recent paper, Ari did say these were difficult to calculate, to compute. And that's true. They're non-trivial to actually do, but at least there's an actual analytical formula for them. You could, in principle, have actually having to do it. So those are what they actually physically are. They're a bit of a mess. You don't really want to write them down too often, but you can actually prove that. And you can then they do satisfy everything of what you expect polynomials to do. They have the interlacing of all the zeros. It's just as you increase the time, the oscillations become bigger and bigger. And what you also notice is you increase time, all the zeros here are quite well spread out in this interval. By the time even the t's got to 5, you can start to see that they're turned to congregate about points here. And we do in fact can prove that they do congregate. They coalesce all into one. As the time increases. So, now what you can also do is if you take these discrete Palomé 1 and you take beta naught to be naught, then you can prove there's a unique choice of beta 1 so that you get a positive sequence. And it happens to be exactly the one you have for writing from the Freud polynomial. It's a unique one. Now, it's very, very susceptible to the initial conditions. So I'm going to show you some plots of where I've taken the beta 0 to be 0 and the beta 1 to be this function, or plus or minus 10 to the minus 4. I've used 250 digits of accuracy to get these plots. These are what with epsilon equal to 0. These with perturbation of 10 to the minus 4. Which I think demonstrates they are sensitive to initial conditions. At least by the visual proof. You can see that they're quite different. There's no patterns at all, but if you get exactly, you do indeed get exactly what they're predicting. Okay. Now you can get an asymptotic expansion. It starts with the square root of n over 12, and then you can work out more terms in it, and so your generalized results, they have the case when the lambda is minus a half, these earlier work. So you can actually explicitly get, and you see that the effect of the even and the odd, they do tend to the same in the end, but it takes a long time. This time it's quite a slow decay. It's only certain. So now let's look at this sextic weight. So we're now going to take order 6. The first thing to do is to look at what mu naught is, the first moment, the lowest order moment. Well, it turns out it's solved in terms of hypergeometric functions, but 1f2s. So the 1f2 satisfied a third order equation. So in the past, all the weights I've had have satisfied second order differential equations. So now I've got a third order differential equation. And the mu naught itself satisfies this third order equation. Prove that quite easily. It satisfies this third order equation, which has this as the solution that you need with all the benevolent initial conditions. Now, something more about this. So really this should appeal to Aria because his favourite function appears. But if you take lambda to be minus a half, then this integral is in terms of squares of every function. Again, that's an indication it was a third order equation. Because there's a well-known result that if you take the square of the product of two solutions of a linear second order equation, they satisfy a third order equation. You see in Whittaker and Watson, for example. Probably a tripos question here in the 19th century. So you can get area functions for lambdas minus a half. So it is an even weight, so that all, and does satisfy as well that you have the kth derivative of mu naught is mu 2k, mu 2k plus 1 is mu 2k with the parameter increased by 1. So I can write all the Hankel determinant in terms of just the Hankel determinant an. And so what you have now is the monic polynomials. You can work out explicitly again what all these coefficients are. Now in this Wronski where this mu naught is now in terms of these 1f2s. Very similar to the Freud weight, the recurrence coefficients have a similar kind of pattern. They differ between even and odd, but this growth here is now like a multiple of the square root of n rather than n, and they also have this behavior here as well. The orthogonal polynomials are very similar to what happened in the case for the Freud weight. They're nice, quite well spaced for small time. As time increases, they tend to congregate on the roots of one place. And again, they just look very similar to what I have in the Freud-Wright case, in that you can actually have the oscillations just increase as time goes, as time increases. So the different plots here are just at different values of time. So now, if you take the Freud-Wright, so the generalized Freud-Wright with order 6, now it satisfies a fourth order discrete equation, which is actually called dp2. It's the second equation in the discrete panel of A1 hierarchy. If lambda is -1/2, the limit is the second member of the panel of A1 hierarchy. If lambda is not -1/2, it's the second equation in the panel of A2 hierarchy. It also satisfies the Volterra lattice equation, and it satisfies this system of two second order equations for beta n and beta n plus 1. I haven't managed to get it down to a single fourth order equation yet. I suspect I will eventually, but that's as far as I've got so far. You can derive this using the Volterra lattice equation and the fourth order discrete equation. You can actually work up this actually for. You can actually get all those explicitly. You can work out the asymptotics. Say the difference is that you've got decay like 1/t in all regions except for the odd ones going towards plus infinity when it's square root of t is the growth. And in this case now, as large n is looking by the third root of n. So, what have we seen? We've seen for the quartic, you've got the mu naught in terms of parabolic cylinder functions, but actually you could write that as a product, as a sum of two confident type geometrics. For order 6, you get 3 1f2s. Order 8, 4 1f1s, 1f4s. So 1f3s, is there 4 of them there? There's 4. There's one of them. There's 4 of those, and they're to give you 1f3s, which satisfies a fourth order equation. Plots look the same. Well, they're similar anyway. You can get, but now the growth is like t to the third. If you go on to 10, 5, 1f4s. So you can actually speculate that the general one in terms of an nth order equation. Okay, so that's, I've done some things like this. Now, we have 2 ways of trying to calculate the recurrence coefficient beta n. I can either use these for symmetric weight, use these Hankel determinants an and bn, or can use the delta n. There's 2 possible ways of doing it. So I'm just going to take this simplified Freud weight and show what the results are to differ what you go between them. If you take the first way, I take the first 16 recurrence coefficients for m equal 1 to 4. If I got an and bn method, this is time in seconds. These are all less than 1 second, even this one that takes 20 seconds. If you use the delta n, this is what Maple gave me. You can see that the difference here is quite huge. So using this splitting of the delta n matrix into 2 Hankel determinants made a huge difference. If I go to the first 20, and these are the results here I get, that you have this huge difference between using this splitting method or using the delta n. So I mean, now I've got, this is just what the, putting a timing, when I did the calculations in Maple, you can set the clock to 0 when you start the calculation, you know the time at the end of the calculation. Just list it on the computers how long it's taken, and they're quite different. So suggesting that from a computational point of view, to use the split between the AN and BN is certainly much better than what you have. Thank you.
Peter, in the last part, when you generalized these Freud weights, you saw that in the first case, the Bn had the recurrence, which was the first member of the discrete level. Can I try to go reverse it? So I have the discrete level 1, and then I go to the first member of the hierarchy, and then I go backwards, and I find what weight it corresponds to this, etc. Will I get any interesting weights this way?
If you can do it, if you do the inverse problem, yeah. You're an expert in inverse problems.
No, but this is not how you do it.
No,
How did you generalize? Why did you make this particular generalization yourself?
You mean why did I keep going up the? You mean the order of the in the exponential?
Index, yeah.
I just want to look at symmetric weights. Aria came to taught me.
And by the way, you all told us all in the first one, are the higher ones also members of the higher discrete level hierarchy?
I believe so. Yes. I mean, then the next one will be in order the third member of the hierarchy. Yes. I mean,
You expect that it will be true in general, which is a very nice result.
I can write the equation down, but I think I can conjecture what the equation is, but I haven't proved it yet. But I mean, I think you will do it as you keep going up. You just keep going up the discrete Pavlov one higher. What the differential equations are is a different matter at all. I'm not sure about that at all.
I understand.
But the discrete one, I think you can go up.
That's very nice.
Do you mind going back to the picture where you have the generalized Freud weights as t increases and the zeros are kind of going to the same spot?
You mean that one?
Yeah. So, do you know as a function of t where
It's in the paper. I didn't know. I can't remember exactly, but it does go to a certain. What we did was we normalized it so the point was 1.
Okay.
And that's just a rescaling because that.
Because if you look at integrals against e to the minus to this weight, the saddle points actually will be somewhere like root t on 2. And
I can't remember offhand. I have to look in the paper what the value actually was. They don't go to the same one. I think it's related like the square root of 2 or something like that.
okay.
I'm pretty sure it is that, but we just made it. We normalized to make it be 1 because 1's a very nice simple number.
Yeah. And then another question is when you have these differential equations for the Hankel determinants, do you ever use the symmetry of the weight, or this could be done with?
I've not used the symmetry of the weight in the Hankel determinant. I mean, the point of the Hankel having the equation of the Hankel determinant is you can do a lot of things with the differential equation in terms of asymptotics, etc. It's much easier to do it from the differential equation than probably anything else as well. I mean, the actual Hankel determinants themselves, you can show satisfy a 4th order bilinear equation. You get that by differentiating the second order second degree, and then putting the logarithmic derivative in, and you get a 4th order bilinear equation. Just a curious fact you have with integral systems. See, whenever you play with integral systems, these magic happens all the time. That's why I love working with them, because you know that magic will happen.
Okay, I have 2 questions. The first one, the Heine formula is a bridge between orthogonal polynomials and random matrix theory. Mostly stuff, if you look at Percy-Dives's work.
Yes.
So essentially, whenever you have a system of orthogonal polynomials, you can say something about the Heine determinant. You can say something about random matrix theory for some distribution.
Yes.
So what is the implication here?
That's a good question. question.
I don't know, I haven't looked at it. I mean, I just purely used the Heine representation because it gave me the differential equation even without having to do any more work.
No, but it's a good project to give it to a student.
It
You
is a
will
good-
find, you will find nice results. You will certainly be a nice correspondent, no doubt.
Yes.
I mean, he's often quoted, I mean, I think in Shogo's book, he sort of says the formula is useless.
Well, this is
But
one of
it's
the
not-
most beautiful formulas.
We can't use it to do much with orthogonal polynomials.
Yes.
Well, except that you can, because I did it.
But you had a second question.
Yes. The second question is, have you tried, and this will be completely useless for my applications, but have you tried to do something with atomic weights, say Q weights?
No, not yet.
Because this can be interesting.
No, not
So many of these problems come from the classical Pavlov equation, second order.
Yeah.
If you go, say, modified KV hierarchy, for second hierarchy, then you'll get a higher order Pavlov type equation. Can you then find the equivalent sigmas and whatever the orthogonal polynomial structure might be? Has anybody looked at
I
that?
haven't looked at it. It's a very good question. I mean, yes, I believe that the answer will be yes. There will be a sigma, which will be a higher order sigma of some
Right,
description. But
right.
the answer is, I think.
And then for
I
the
don't-
simplest one, you don't want to go
I mean,
to the higher ones.
I
Do
mean,
first.
this was when I did the degree 6 weight. You got the third order equation, and then actually that third order equation satisfied a second order nonlinear equation, whereas I used to take in the second order equation in Riccati, so you're definitely going up. So this is beyond Pan-Levet.
Yeah, but again, maybe the same hierarchy.
It'll be in a hierarchy of Pan-Levet, yes.
So this will be a nice closure. I mean, you will have families,
Yeah.
which will be very nice.
I think it would just go up as in a hierarchy of families. So
Very
once
nice.
you've worked it out to the second one, you've probably worked out the entire hierarchy. Once you saw that pattern, I went 4, 6, 8.
But this is why I suggest it would be a very nice way to create then a mathematical way of creating family of weights in a sort of natural maybe way.
Okay. If there are no further questions, thank you very much indeed.